Okay, so I'm going to go over a pretty quick PowerPoint. This is provided by the publisher of the book, your Green Building Principles and Practices book. And so I'm just going to narrate some of these PowerPoints just to give you, some of this will be a review of concepts you've already gone over, and then some of it will be a preview of this week's content. So Chapter 2 is all about house as a system, as you can see. And before we begin, actually house as a system is a really important concept. So house as a system is this understanding of how buildings work. And it's important that you understand that all of the components of a building are interconnected. So something that happens in the basement can impact what's happening on the attic or on the roof. Something on the second floor can impact something that's happening on the first floor, and so forth. So that's thinking of the whole house or the whole building as a system. This also applies to commercial buildings as well. And remember, building science is the study of all of this interaction between all of the building systems and components in a building. So everything we do in this class is building science. Again, this is a review, potential and kinetic energy, and then we went over some of the common energy units like CCFs and kilowatt hours and gallons for fuel oil and so forth. So all this stuff you should be familiar with by now. We've gone over the first and second law of thermodynamics. Remember, the first law is that energy is not created or destroyed, it only changes forms. The second law has a couple, remember that's about entropy, but the implications for our purposes are number one, that heat always flows from areas of higher to lower temperature, and number two, when you convert energy from one form to another, there's always some loss. It's always less than 100% efficient. So there's no such thing as a 100% efficient furnace or boiler. Okay, so that's the first law and the second law. All of these apply in a lot of different ways to energy and other systems in buildings. So remember, we've talked about temperature is the average kinetic energy of molecules of a substance. We have discussed heating degree days. We haven't really discussed cooling degree days, but they're just, think of the sort of opposite of heating degree days. Remember, heating degree days are sort of generally how much heating you need, how cold is the climate. Cooling degree is just the opposite. So if you have a lot of cooling degree days, that means you have a pretty warm climate. You need a lot of cooling, and the maps of those two, HDD and CDD, would be pretty opposite, and they would roughly match up to the climate zones. So remember, heat flow, the heat's always going from the warmer to the colder areas, and remember, there's three methods of heat transfer: conduction, convection, radiation. We've gone over that before, so I'm not going to review. You should know what those are by now. Right? So conduction requires physical contact between two different things. It could be within a substance or between substances. And then R value, which we've also gone over, that's the measure of the resistance to heat flow. Remember, R is resistance. So more R is better. And remember, the inverse of that is U value, right? So U is 1 over R, and R is 1 over U. Again, this is a review. And that the U value is the thermal transmittance or transmission. And so this is transmission, so you want lower U value because that's less transmission, which means it's more insulating. Okay? And this is something that we'll do in lab and some other assignments. And remember, we have our basic heat loss formula is UA delta T. We'll use that a number of times this semester. Very, very important formula in energy management and energy building design. If you're building a house or a commercial building, you need to know all the U values of the various surfaces, and then you kind of look at the temperature difference between the two, and then that'll tell you at any given point what your approximate heat flow is. And you'll see this, that we'll use this later in the semester when we do HVAC design, because you basically want to design a building so it can be heated to an acceptable temperature at the very coldest time of the year in that climate. And to do that, you definitely need to understand heat flow and definitely use this UA delta T equation. And remember, that's BTU, U is BTUs per square foot per hour per degree Fahrenheit. And it's the amount of heat that flows across a 1 square foot surface over 1 hour when there's a 1 degree temperature difference on either side. And then seasonal heat flow, again, we've gone over this already. Seasonal heat flow is very similar to the regular heat flow equation. It's UA which is the same, and then it's HDD and then times 24. So remember, that's a conversion. So this is if I want to calculate the approximate heat flow through a surface over the course of an entire year, I need to know the HDD. Okay, so this is something we're doing in lab. And once you do that, you multiply the HDD times the U value times the area times 24, and that'll give you your approximate heat flow throughout the year. Now keep in mind this is approximate, but it gives you a really good approximation. Okay, and just as an FYI, because U is 1 over R, right? So you can apply the same formula. Say if U equals 1 over R, so the same formula is A times HDD times 24 divided by R. It'll give you the same result. Okay, so that's your conduction. So that's, remember, through a building envelope is mostly conduction, conductive heat transfer, although there is some convection and radiation. Convection is when heat is traveling with a fluid. Most often we refer to convective currents in the air, but you can have it in water as well. That happens when you have a hot water heater, for example. You have these little convective currents inside. It's called a thermosiphon. But you can also have forced convection like you do in a forced air furnace. Like if you blow a fan, that's forced convection. And convection is important. We'll talk about this in more detail and when we talk about the stack effect and ventilation. So when you force air into a building, an equal amount of air must go out of a building. And we'll talk about that implication throughout one of the lessons. And then the third method of heat transfer is radiation. So remember, everything around you is radiating energy all the time. Everything above absolute zero radiates energy, just like everything above absolute zero has thermal energy, right? So the vibrational energy of the molecules. And then radiation goes out, and we haven't really discussed this in too much detail, but there's really one of 3 things that can happen once it hits a surface. It can either bounce off of that or reflect. It can be absorbed by that surface, or it can be absorbed and then transmitted, so absorbed and re-released by that surface. And that's the basis of an important part of the greenhouse effect, which we'll talk about as well. And so remember, solar radiation is one of those external heat gains that can end up causing passive heating inside of a building. And we'll address passive heating design, or passive design, later on in the semester. But using windows and solar heat gain is a really important part of passive design. So you want to kind of keep an eye to that because we will discuss how we can use that, take advantage of that to do some passive heating in the winter by allowing sunlight to come in. There's different types of windows that will sort of block some of the sunlight in the winter and then allow a lot of the block some of the summer sun but allow the winter sun in, and we'll talk about that as well. We've gone over a bunch of the different fuel types, so I'm not going to spend time on this. We know that the main ones that we use where we are, natural gas and electricity. There is certainly a lot of fuel oil out there. Propane, a little more common in southern parts of the state, but mostly natural gas and electricity with some fuel oil. And now you know how to convert those to different units. So this is more relevant to what we're going to talk about this week, and that is airflow. Air always moves from areas of high pressure to areas of lower pressure. So just like heat moves from higher temperature to lower temperature, what causes air to move is air simply moves from areas of higher pressure to areas of lower pressure. Okay, and so if you have 2 different pressures and you have air that can move in between, that air is going to move until it equalizes to reach kind of an equilibrium. So just like with heating, the heat's going to keep flowing until there's an equilibrium and there's no temperature difference or no delta T between the 2 areas. Same thing's going to happen with airflow, and we'll talk about that as well. So nature's kind of trying to gain equilibrium all the time, where you have a higher temperature here, a lower temperature here, the heat's going to move from higher to lower. Higher pressure here, lower pressure there, it's going to try to move over to the lower pressure. Okay, and so this actually is a really common phenomenon within buildings, but also between the building's interior and exterior. And we'll talk about the stack effect in more detail, so I'm not going to get into it here, but they do detail that in your book. It's just basically warm air rising and then forces the air pressure higher toward the top of the building and lower at the bottom of the building, which forces air out toward the top and brings air back into the bottom. So I go over this in more detail in a presentation in class. So moisture flow, I'm not going to spend too much time in this. We're going to go over this in a later lesson. But there's sort of two types of flow. You can have bulk flow, which is liquid, and then you can have vapor flow, which is there's always water vapor in the air. And so when air moves around, water vapor moves with it. Again, I'm not going to focus on this week. We'll talk about that in more detail. Bulk moisture is, you see like liquid water in a house or another building. And there are different barriers that you can use that sort of block a certain percentage of water vapor. And that's sort of these vapor retarders that you can use in certain parts of the building. And they're based on this thing called a perm rating, which is basically how much it allows, how much vapor it allows through. Again, I don't want to focus on this, on relative humidity. We'll talk about this in a later lesson, so I'm going to kind of skip through this. Dew point and condensation, we'll talk about that in a later lesson as well. Dew point is just the temperature at which water condenses out into a liquid from a vapor, and you have to cool it down to reach that point. So every air has always has a dew point. So you can cool any air mass down to a certain temperature, and it's going to start condensing out liquid water. And we'll talk about that in more detail later. We'll focus this week on air sealing. So air sealing is a really important part of making a building more efficient and passive and reducing your energy use. You want to control air movement as much as possible. Okay, so you can't control everything, but you can do everything you can to try to control air movement. So you do a lot of strategic air sealing in buildings. If you're building a brand new building, you want to make it really tight. We'll actually talk about passive design standards, which are really, really tight to the point that you have to bring in fresh air all the time. But most buildings are leaky enough that you generally bring in enough fresh air for residential buildings. But we'll talk about some sort of trouble spots where air is really commonly leaks in and out of buildings, and then sort of how you fix that. So we'll address that this week. And I'm not going to get into the psychrometric chart. You can kind of log that away. We'll talk about that when we look at humidity and relative humidity and its relationship to air conditioning. You may know that if you cool down air to a certain point, you can dehumidify it, and that's the relationship between relative humidity and condition. As you cool the air down, the relative humidity actually jumps up until you reach past the dew point, and then it pulls moisture out of the air, which then drops the relative humidity. So we'll talk about that in more detail later. We've already addressed the building envelope. Remember, that's the line between conditioned and unconditioned space in a building. Often, it's also usually the thermal envelope, and it's not always. Remember, it's not always where you think it is, because sometimes you might have a building on like a roof that's just the building. That's just the building shell, excuse me, but that might not be the building envelope. The building envelope is generally where the insulation is, assuming there is insulation in the building. Okay, and a good thermal envelope or a good building envelope will have a thermal barrier and an air barrier continuous and in contact all the time. And we'll talk about that as well. Right, so building envelope, you can clearly see where it's supposed to be, and that's where the insulation is here. But you can see there's also a little bit of a break in the building envelope here because there's some drooping insulation, which means it's not that thermal and air barrier aren't continuous and in contact. So that insulation should be consistent and constant throughout the entire envelope. And if you have a little bit of a hole, a little bit of a gap, that can really compromise your insulating value. We'll talk about ventilation and its importance. It's a little less important in most residential buildings, very important in commercial buildings, but you need fresh air for the people in the building. Okay, and the tighter you make a building, the more important ventilation is, because if you have a really, really, really tightly sealed building, you're not going to get much fresh air in there naturally, and so you need to add ventilation. And commercial buildings have actual codes and standards that require a certain amount of ventilation, and we'll talk about that and do some calculations later. With residential buildings, it's a little less important, but some buildings do need ventilation. And there's just a couple of different kinds of ventilation, spot ventilation, and there's exhaust fans that are sort of constant whole house ventilation as well. And that's all part of indoor comfort. So indoor air comfort is really important part of having a nice building, residential and commercial. And so that includes everything from your relative humidity to your temperature, to your fresh air. We'll talk about that in detail throughout the semester. And again, a lot of this has to do with relative humidity, so we'll address that in a later session. Okay, so that's it for the Chapter 2 overview.